To close out the chapter on differential equations, I'm going to talk about a special kind of problem called exponential change. All exponential change problems read as the following. The rate of change of y is proportional to the quantity of y, and k is the constant of proportionality. And notice that we're differentiating with respect to time now because this is a rate of change. And as you know, rates are per unit time. Let's solve this equation and see what our solution looks like. I'm going to begin by removing this dt from the denominator by multiplying by dt on both sides, like so. And then I'm going to move this y to the left, like so. And we have all our y's on the left and all our t's on the right, so we can integrate. When we do this integration, we get ln of y equals kt plus c. Now it's just we have to algebraically solve for y. We're going to take both sides to base e. So we have y equals e to the kt plus c, which we can simplify to e to the kt times e to the c. But as you know, this is still c. So this is the most popular form of the solution. It's y equals c e kt. So this is the general form of all exponential change problems. And you'll notice that here we have two unknown constants, c and k. So that means we need two initial conditions to solve exponential change problems. The only exception to this is when it's a chemical half-life problem, where we have a formula to find k from half-life. One final thing,
there's two kinds of exponential change problems.
There's growth and decay. And the type is determined by the sign of our k, the constant of proportionality. If k is positive, then it's growth. If k is negative, then it's decay. And just so you have kind of a picture, this is the graph of a growth function, and this is the graph of a decay function. I'm going to do two examples for you. First one is like a standard exponential change problem, and the second one will be one with half-life, where we'll go over the formula for k and how to solve it. So in this problem, we're told the rate of change of vehicles on a bridge is proportional to the number of vehicles on it. If at time t equals 0, there are 100 vehicles, and at time t equals 10, there are 20, model the number of vehicles on the bridge. Let's write down what we're told first. So right away, we're told the rate of change, I'm going to say v for vehicles, the rate of change of vehicles is proportional to the number of vehicles on it. This is our differential equation. We're given an initial condition at time t equals 0, there are 100 vehicles, or v of 0 equals 100. And our second initial condition is at time t equals 10, or v of 10, there's 20. So we have v of 0 is 100 and v of 10 is 20. Before we can use this information though, we have to solve this for v. I'm going to multiply dt on both sides, like so, and then I'm going to move this v to the left, like so, and then I'm going to integrate both sides, and I'm going to algebraically solve for v. But we all know where this is going. This just goes to v equals c e to the kt. Using this, now we can apply these initial conditions to fill in numbers for c and k. But now the question is, which one should we use first? Keep in mind, we have four unknowns, v, c, k, and t, but we're only given two pieces of information at a time. So we need to choose something that eliminates a third so we can solve for the last one. The only one that does this is here, v of 0 equals 100. Because when we apply this, if you multiply k by 0, it's 0. So we don't have to know k to find c because of this initial condition. E to the 0 is 1, so I can get rid of this. And now we find that c equals 100. So I'm going to substitute 100 into the equation here, like this. And now we can just normally substitute this to solve for k, like this. And now it's just a matter of algebra. And through this process, and with a little bit of help from a calculator, we find that k is approximately negative 0.16. When we substitute this number into our expression here, we get the final answer that V equals 100 times e to the negative 0.16 t. Notice that this is a decay function. So the number of cars on the bridge is going down with every passing moment in time. Now it's time to do our half-life problem. So we're told that the half-life of an unknown element is 24,100 years. Given that 350 grams of it was found, we need to model the remaining quantity with respect to time. Let's write down what we know. The keyword half-life indicates an exponential change equation. So I'm going to say that the rate of change of this element with respect to time is proportional to the quantity of this element remaining. We're also given an initial condition. Is 350 grams of the substance was found, or E of 0 equals 350. Let's go ahead and solve this differential equation and see what our solution looks like. As per usual, I'm going to multiply both sides by dt. Then I'm going to divide both sides by e, and here I'm going to integrate both sides, like so. And of course, we can algebraically solve for e, but we know that it's going to end up as e equals ce to the kt. We're going to use the only initial condition that we have to see if anything is going to happen. So we have 350 when t equals 0. And this is the same as last time. We're eliminating k without actually knowing it so that we can solve for c. K times 0 is 0, and e to the 0 is 1. So we can effectively just get rid of all this. And we see that 350 equals c. But now it looks like we have a problem. We've run out of information, and we still have an unknown here. This is where our half-life comes in. There's a special formula in this case for k when we're given a half-life, and that's k equals the natural log of 1/2 over your half-life. In our case, this would be ln of 1/2 over 24,100, which is approximately negative 0.00003. Very small constant of proportionality, but that makes sense when you stop to think about just how big our half-life is. When we substitute this value back into our expression, we get E equals 350 times e to the negative 0.00003 t. And that's our model for our element.